we're going to get to where we're talking about electron configurations. This is a shorthand way of denoting how the electrons are distributed in an atom. And there are three things that we want to start out talking about. The Pauli exclusion principle, the Aufbau principle, and also Hund'sRule. The Pauli exclusion principle says that no two electrons in the same atom can have the same set of 4 quantum numbers. Remember N, L, M sub L, and M sub S. So no two electrons in the same atom can have the same set of 4 quantum numbers. The Aufbau principle, which comes from German for to build up, says that when electrons fill atomic orbitals, they go into the lowest available energy levels. There are two ways to go about remembering the energy, the way that electrons fill into these orbitals in terms of energies. And you may have seen, and there's in most books, a little chart that looks something like this. One S in the first row, then 2S, 2P in the second row, 3S, 3P, 3D in the third row, and so forth. And so the order of filling goes along these diagonals. The electrons first go in the 1S, then the 2S, then into 2P, then 3S, then 3P, and 4S, then 3D, 4P, 5S, and so forth. The other way of remembering is just simply read it off the periodic table. That if you remember that those two columns are the S block, if you stick helium over there with that, these 6 columns become the P block. These 10 columns are in the D block. And these 14 columns are in the F block. And so we start out with N equal 1. Gives us hydrogen and helium. There's no 1P. That violates our rules for solving those wave equations. Then comes N equal 2, so you just go in order of increasing atomic number. So that would be 1S, and now 2S. And then we jump from beryllium over to boron. No 1P, we're now 2P. Then back to 3S with sodium and magnesium. We don't encounter any Ds yet, so the next row going across from aluminum to argon are 3Ps. Go back from argon to potassium. These become the 4s. Now we're in the D block. The S started with n equal 1. The P start with n equal 2. The D start with n equal 3. So these become 3D from scandium across to zinc. And as we go from zinc to gallium, we now cross back in the P block. So some gallium to krypton will be 4P. And then we go back over the left side of the table, 5S. We've used 3D, so now we are at 4D. As we go into the P block, 5P. Back to the S block, 6S. Then 5D. And then 6P. Back to 7S. 6D. And 7P. Now along the way, I've skipped over the F's, and from like cerium to lutetium, they fit in between lanthanum and hafnium. And we're in the F block. S has started with 1, P start with 2, D start with 3. So these are the 4 F's. So they fit in between the 6S and the 5D. And so if you look down at our chart below, there's 6S and there's 5D. What's in between is a 4F. And likewise, in between elements number 89 and 104, we've got 90 to 103. And those would be the 5Fs. And so you can either remember this chart and draw your diagonal lines and follow that along, or you can just read it off the periodic table. That's the way I like to do it, but you're certainly welcome to do either method that you want to remember the order for filling electrons in terms of energies. One last thing to talk about, Hund's rule. And that says that when orbitals of equivalent energies are available, when filling orbitals, electrons go into separate orbitals. Another way of saying that is they remain unpaired. It's like when you get on a bus, and if you know no one on the bus and there are empty seats available, what do? You go sit in an empty bus seat. And so with their orbitals of equivalent energies, this will make more sense when we actually do some examples. Those electrons will go into a different orbital as opposed to pairing up and sitting on a bus seat, so to speak, with another electron.